to give me this opportunity to be here in the nice workshop. I would like to present something about the symmetry breaking of maximal outer planar graph, regular, and Cayley graphs. Okay. As all of you know, the distinguishing number denoted by dg and is the least number d, such that g has admits a vertex coloring that is only preserved by trivial automorphism. And 19 years later, Raphael and Monica introduced this distinguishing index as edge labeling or coloring. And I think the first papers in this subject has been about the computing the distinguishing number and distinguishing index for some specific graphs such as cycle, path, complete bipartite graph, and so on. And actually, we could to obtain some result for another specific graph, such as a friendship graph. You see here, the friendship, as you know, is the join of K1 plus and K2, which and has this figure. And you see here the distinguishing number of this kind of graph obtained by this ceiling number. And for the distinguishing index, the number is much harder. And you see here, we put A and this number, and then the distinguishing index obtained by this ceiling formula again. And also we could obtain some another result on these two parameters, such as what happened to distinguishing number of a graph when we remove a vertex, which we contract an edges, and something like this. As you see here, for example, when we remove a vertex of graph, then distinguishing number decrease 1 and increase 2 times dg. And also we have the same situation for distinguishing index. And you see, for example, something about the distinguishing number of graph when we remove an edge from the graph. You see here that the distinguishing number of graph increase 2 and decrease 2 again. Okay, and we can ask about another question, another operation on graphs. For example, a contraction of a vertex. And you know the contraction of vertex means that we join all neighborhood of the vertex together and then deleted a vertex. And you see here distinguishing number of this kind. This operation is greater than or equal dg minus 1, and you see the relation for distinguishing index. And these inequality are sharp. Okay, let's go to main subject of this presentation, which is about maximal outer planar graph. Just I recall some theorem and result about the distinguishing number of planar graph that Arvin and Diviner in 2004 proved that the distinguishing number of planar graph can be computed in polynomial time. And every three connected planar graph is 5 distinguishing colorable, except these two kind of graph. And here we need the definition of radial graph that denoted by capital R, G, which is defined as the graph obtained as follows. Put a vertex in H in every faces of the graph, join it to all vertices lying along the boundary cycle of the face, and finally delete all original edges of the graph. And you see a nice theorem here about three connected bipartite planar graph, which are three distinguishing color, except this two kind of graph, cubic tree and the radial graph of Q3. Okay, and you know a maximal outer planar is an outer planar graph that cannot have any additional edges added to it while preserving outer planarity. And also you know that this kind of graph with order n must has exactly this number of edges, and obviously every bounded faces must be a triangle. And this kind of graph satisfies a stronger condition than Hamiltonicity, which is pancyclic, means that for every vertex v and every k from 3 to order of graph, there is a cycle with length k containing a vertex v. And you see here maximal outer planar graph with 7 or less vertices that you see has a recursive construction. Okay, to study the distinguishing number of maximal outer planar graph, first we must prove this theorem that says if it is a connected graph with clique number 4 and maximum degree delta greater than or equal to 5, then distinguishing number is less than or equal to delta minus 1. And this condition is necessary. As you see here, we have an example for a graph with delta chi, okay, and d equal to them, and as all of them are 4. And so by the previous theorem, we have this corollary that if this is a connected planar graph with chromatic number 4, and also with this condition, then distinguishing number is less than or equal to delta minus 1. Okay. And if this is a connected graph of order n greater than or equal to 6 with exactly one Hamiltonian cycle, then distinguishing number is at most 2. And so if it is a maximal outer planar graph, then distinguishing number is at most 2 except for K3. And we have the same result for distinguishing index. Okay. Here we consider Halling graph. Halling graph is constructed by connecting the leaves of a tree into a cycle. The tree does not have vertex of degree 2 and at least have 4 vertices, and it should be drawn in the plan so that none of its edges cross, and the cycle connects the leaves in there connectwise, ordering in this embedding. And obviously every Halling graph has a Hamiltonian cycle, and you see here all Halling graphs of order 6 or less again has a recursive construction, I think. Okay, to study the distinguishing or symmetry breaking for the Halling graphs, we should have this lemma that states if it is a tree of order at least 4 with no vertex of degree 2 and G be its Halling graph, then if F is an automorphism of G fixing the vertices of the cycle induced on the set of the leaves of 3T, then F is identity automorphism of G. Okay, we use this lemma to prove this theorem that if T is a tree of order at least 4, with this condition that no vertex of degree 2 and GB is Halling graph, then distinguishing number of Halling graph is at most 4. Okay, and we can improve this upper bound with this extra condition that you see here. If the T has no vertex of degree 3, then we can improve this upper bound to 3. And again, if we add another condition that you see here, the number of leaves of the tree is at least 6, then distinguishing number of Halling graphs is at most 2. Okay. And this is about the distinguishing index. If there's a Halling graph, then distinguishing index is less than or equal to 2, except for K4. Okay, and I think the last families of graph that I consider here is Misilsky graph. We have a graph G with n vertex, with n vertices V1 and Vn. Misilsky graph denoted by mu G and contains G itself as an isomorphic subgraph. And we add n plus 1 additional vertices. For example, we add U1 corresponding to V1, U2 corresponding to U2, and so on. And also we have another extra W, vertex W, and this W connect to all of the UI, okay? And we have another condition. If Vi is adjacent to Vj in the graph G, then in the Misilsky graph of G, Ui must be adjacent to Vj, and also Vi must be adjacent to Uj. And you see an example here, Misilsky graph of C5. We have 5 vertices here, and we add 5 vertex corresponding to this Vi and another vertex W, and then W must be joined to all of the vertices Ui, and because of these edges which there is here, we add some edges here and between Vi and Vj. And you know arching graph, I forgot to say, we recall that graphs with no pairs of vertices with the same open neighborhood called arching graphs. And here, if we have a theorem that says if G is the arching graphs of order n greater than or equal to 2, then the distinguishing number of Misilsky graph of G is less than or equal distinguishing number of G plus 1, and this inequality is sharp. And also, we have the same for the distinguishing index. Okay. Now we want to see what happens to graphs when we repeat recursively Misilsky graphs. You know, for example, you see we start with a graph with a single edge and produce a sequence of graphs Mi, which is mu mi minus 1. And it is easy to see that these kind of graphs are arcing. And so we are able to compare these two parameters. You see here the distinguishing number of mi is always less than or equal to dm minus mi minus 1. And also is true for distinguishing index. Okay, and as you see here, the distinguishing number of this kind of graph is exactly 2 for every I greater than or equal 4. Okay, and as I said before, we proved that the distinguishing number of mu g is less than or equal to dg plus 1, but we think that we can improve this upper bound. That remains as a open problem or conjecture. And also, we think this is true also for distinguishing index, except for a finite number of graphs. Okay. Here we consider the symmetry briquet for regular and Cayley graphs. All of you know the definition of the Cayley graph. Given a group H and closed subset S under inverses, which S do not contain 1, the Cayley graph denoted by KH and S is the graph with vertex with H and H from H to SH. Okay, the automorphism of this kind of graph contains the right regular representation as a subgroup, and so this kind of graph are vertex transitive. And it is so easy to see that the distinguishing number of Cayley graph is between the number 2 and cardinally S plus 1. And if this Cayley graph is a normal graph, then distinguishing number of Cayley graph is less than or equal this number. And if Cayley graph is a graphical regular representation of a H, then distinguishing number is exactly 2. And if the Cayley graph is a normal, which is not isomorphic to these abelian groups, then distinguishing number of Cayley graph is at most 3. Okay. And if automorphism group of Cayley graph acts on H primitively and gamma is not complete, then distinguishing number of Cayley graph is exactly 2. Okay. And here you see some result on regular graph. Let gamma be a K regular. Obviously if K is less than or equal 4, then distinguishing index is less than or equal 3. And if K greater than or equal this number, then index of this K regular is exactly 2. Okay. And the third one says if the Cayley graph, if gamma is a Cayley graph and is a graphical regular representation of H, then distinguishing index is exactly 2. And if the connected K regular, then d prime G is less than or equal to 3. And we have this conjecture that if G is a K regular graph, for K greater than or equal to 5, the distinguishing index should be 2. Okay. Okay, if you let me just, I want to present some upper problem and my conjectures, which are not related to this topic, but I think you are interested in and may we have cooperation to solve this upper problem and conjectures. The first one that is in my paper with my student in the communication algebra is about stabilizing the distinguishing number of graph. And you know, I think about the distinguishing number, stability of the graph means that how many vertex we should remove from the graph, and the stability should change. Okay, and the minimum number of vertices should be removed is the stability of distinguishing stability of a graph. Okay, and we can have this for distinguishing index, and also for edges that we call it bondage number. And this is our problem that give Nordahl-Gaddon type inequalities for the bondage number of distinguishing number of graph. And in this paper, we characterize the trees with distinguishing number 2, and we have a problem that characterize edges which add to each edge minimal to self. Connect the graph such that the distinguishing number of complement of the tree is 2. And actually, we studied the distinguishing number and distinguishing number for natural and fractional power of graph. You know, I am not sure that you have seen about the fractional power of graph, which is has a nice definition, and we could obtain some result about distinguishing number and index of this kind of graph. But actually, we could to prove that distinguishing number of G power 3 is less, the distinguishing number of G2 is less than or equal to 3, but we think we can improve this upper bound by 2. And thank you very much for your attention. Thank you.
Yeah, thank you very much for your talk. Are there questions for Saeid?